This here is page 8. Let's get to it. All right. We are going to get these questions done. Shh. You are still talking. Please stop that talking that you are doing. Now, please remember there are a few different ways to explain induced EMF and hence induced current, which produces induced magnetic fields. I have borrowed, some may say stolen, this image from a textbook because it is an absolute banger. Remember, this is the topic that lots of students struggle with. Now, it might only be worth 1 mark to draw the direction of current or 4 marks to explain why, but I want you guys hitting this every single time. I don't want you losing these marks. So, remember the template. 1 mark, state the scenario. The 2nd mark, Faraday's law. The 3rd mark, Lenz's law. And then the 4th mark, you then state the consequence. Now, this question, although there are none, the question states, Wilson, Hamish, that we have some conducting metal rings that are travelling in a direction as shown by the arrow. Okay? There are 2 different magnetic fields. One is a strong into the page and the other is a weak into the page. It asks to draw in the induced current, if any, on the rings. So let's eliminate the ones that are not experiencing a change in magnetic flux. Now just hold on. Their area is not changing. So the only way that a change in flux can occur is if the field is changing as they travel. Can we find any where the field is not changing? Which ones? G. G is not changing, nor is H. As it moves, the density of those lines does not increase or decrease. Huh? E. Yes. Even though E is on a border, it's travelling along the border, so the density does not change. With that logic, what else?
C, B, A, F.
Whoa. Slow down. C and A, yes. F, yes. B is changing.
Oh, no, it's going.
All right. So, I think we're good. I would like us to look at ring number L. Okay? This is the easiest one to start with. Some of them are a little bit trickier. Now, guys, this is a static image. We have to imagine that this ring is moving into the field. As the ring moves into the field, it experiences a change in flux, which is directed into the page. Boom, 1 mark. Faraday's law, Lenz's law, and so it's going to produce an induced EMF in a direction such to oppose the change in flux that induced it. We're going to figure that out now. I'm going to write some shorthand to help us. Now, obviously, you wouldn't scribble this if it was a waste question, but I would say that the change in flux that it experiences, so get this written down, please, and let me just drop that thickness down. The change in magnetic flux is going from 0, and let's just write the word 0, to into the page. That is a change of into the page. Now, I just as well could have used the proper final minus initial. I could have assigned a convention that into the page was positive, and then it would be final positive minus 0. You could use that convention. But hopefully you can see that if you started with nothing and all of a sudden you've got into the page, that is a change of into the page. So, then Lenz's law states that the induced EMF will produce a change in flux in a direction such as to oppose that which induced it. A lovely statement. Make sure you commit it to memory. Opposite, opposing, it's going to go out of the page instead of into the page. Okay? So, we then get our right meat hooks out and we are going to say, right, my induced current is the thumb. It's going to travel around in such a way that my fingers inside the coil are travelling out of the page. So if my thumb is to the right, it's going up. If my thumb is at the top, it's going left. It's anti-clockwise, all right? So your fingers are going to show the direction of the change in flux, which is the magnetic field going out of the page, inside the coil, all right? So that's what you do. Your Lenz's law, then your right grip rule, we would get this guy going anti-clockwise. All right? Only whilst it is crossing the boundary. Okay? Whilst it's crossing the boundary, we would see electrons traveling in a, positive charge traveling in an anti-clockwise motion. Yes, okay, the electrons will be traveling in the opposite direction. So, here, allow me to demonstrate this. No, let's try that again. Here is my conducting ring. I am going to auditorily describe to you the induced current as it travels in. Ready? Nothing, 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 nothing. Anti-clockwise, anti-clockwise, nothing, 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 nothing. Clockwise, 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 nothing, nothing, nothing. Yeah? It's only when it's crossing the boundary. And in fact, when I went the other way, everything flipped. The change was flipped, so the induced direction was flipped, the direction of current was flipped. Not only that, that was Lenz's law. I can now show you Faraday's law. I could go clockwise, 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 nothing, nothing, nothing. You know, the loudness of my voice might indicate the magnitude. That's too difficult. Let's get rid of it. Okay. So, let's go to K now. As I just said, if you go into this field, you would get an anti-clockwise. If you reverse the tape, it would be clockwise. Use the same method over for K, please. So, let's, again, my little shorthand sketch here to say that the area bounded by the coil K experiences a change in magnetic flux of into the page to 0. That is a change of out of the page. Okay, so as it crosses that boundary, the change in flux is directed out of the page. Well, Lenz's law says that the induced EMF is in such a way as to oppose the change in flux. Well, wouldn't you know it, that is into the page. So, cool. We're nearly there. Last mark of the thing is, hence, state the consequence. The consequence is that my induced current, fingers need to be travelling into the page inside the ring. Right grip rule will show us that we get a clockwise flow of charge. Okay? Cool? So we'll go clockwise that way. Why did my pen change colour? Let's pick one that is a little bit trickier. This one. It's not that tricky. This one, our change in flux is going from a small into the page to a large into the page. That change is into the page. Okay? It's like you're travelling south and you stomp on the accelerator, now you're going faster, the change is south. Induced EMF is going to be in the opposite direction. Same deal. Right grip rule. Fingers inside the coil now need to be pointing out of the page. So right grip rule, wherever you analyse it, we would get anti-clockwise. Okay? Cool, cool, cool. There are a few others there, and same deal. I've said it out aloud. You might want to do the 4-step response. As coil D enters the magnetic field, it experiences a change in flux directed into the page. All right, get used to writing all that jazz. Okay, over the page, please. We kind of touched on this yesterday, but you have to have a very intimate knowledge of the field lines of a magnet and their directions and their strengths as they get closer or further. So from north, that way, that way, that way, to south, that way, that way, that way, and then we've got the boundaries. Okay? Now, remember we said it's pretty tricky to visualize the strength of the field as a magnet was to approach the sensor, and we did so the other day the question would say as it's moving to the coil, but not entering it, because when it enters, things change. But as it approaches the coil, the area bounded by the coil, so let me just put the area bounded by the coil, is going to experience a change in magnetic flux. It's going from 0 to left, yeah? Because when the magnet is far away, there's no magnetic field, close to 0. As you bring the magnet towards the coil, all of a sudden, we've got left. That is a change in left. So Lenz's law says that the induced current will be in such a direction to as opposed. That's right. Okay. Now we're a side-on view here, but Lenz's law just told us that our fingers, which are the induced magnetic field, must now be pointing right inside the coil. So, how are we going to do that? Maybe I could put my thumb above. So now my thumb is at the top of the solenoid, it's coming out of the page. At the front, it's going down because my fingers are now in the solenoid and they're pointing right. That's all I needed to do. Right grip rule gives the induced current going down like so. Well, have a look at this diagram. It's trying to show us that this wire is at the back. Okay? So logically, if we loop it around,
is that the front or the back?
It's the back. And that's the problem with some of these diagrams. It's not like one of those magic eyes where if you go cross-eyed, it suddenly comes to the front. Hopefully, we are looking, that's the entrance there. Okay? So if that's the entrance, that's the back. Okay? And so the answer for this question is that the current would flow from X to A through the meter. Okay? Again, you will always be given a convention of which direction or draw on the diagram. Again, that's worth 1 mark, and then there might be an explain why that is. Just before we move on, please recall that the magnetic field does weird stuff. Let's just measure the field. Imagine I had a magnetic probe here, right? Just like the one that's sitting over there. And I pass the magnet by that magnetic field probe. So B in Tesla. Now I would need to assign a convention here. So let's go that left is positive and right is negative. Look, I've just assigned a convention. Here's my magnet, left, right, and then left. If we were to bring that magnet towards, we got that weird shape on the laptop the other day. Here's what you get. You get something like that. All right. But then, when you get to part 1, which is the boundary, it suddenly changes. And now it's going right. And then, when you get to section 2, it changes again. And then, as the south pole leaves the probe, it then starts to decrease again back to 0. Okay? So that's what you get. Yes?
Is it reasonable to say using the right grip rule? Like, is that like a reasonable thing?
Yeah. Yep. You could say the right grip rule.
To determine like which way we go.
The right grip rule then denotes. Hang on. Let me just get this a little bit. The right grip. So as per the right grip rule, the current must flow from X to Y. Okay. So, what we were looking at for this scenario here, let me just bring it out. We're really only focusing about this point. Okay, as the magnet is brought towards the coil, but not through it. You have a think, what would happen when it goes through the coil? It suddenly changes direction. So you would say, from my perspective, you would get a anti-clockwise, but then as it enters, it suddenly changes direction. Then it stops, because here, while the magnet is passing through, these field lines are not really changing. So imagine I had a loop, and I brought the loop, along the magnet. You say, well, in this region here, the field lines aren't really changing. The change is only really at the boundary or as the boundary is approaching it. Okay? So they may throw in a nasty question that asks you to sketch everything as it passes through in its entirety. Well, things would be a little bit nasty because remember your induced EMF, if that's B as a function of time, They've done this a few times before. If this was, try again. If this was b as a function of time, that's my graph there, right? There's no equation for it. Weird stuff's happening with a bar magnet. If I said, let's sketch dB by dt, well, hang on, that looks a lot. Let's times it by A and throw an N. Hey, look, that's your induced EMF with a negative out the front too. So let's look at the derivative of that. Well, holy moly. I'm in over my head here. What are we going to do? We'll start at 0 and then it starts to, the gradient like to that, and then it suddenly drops to a negative, and then back to 0. And then this region here, the b by dt is 0, so it's like a flat line. And then all of a sudden you've got a massive positive gradient, so you get this big spike like that.
You get asymptotic.
And then it sort of drops back. You get that kind of shape. Okay? It's tricky. You might have done this in year 10 or year 11 of here's a distance time graph, and underneath the distance time graph, sketch a velocity time graph. And underneath the velocity time graph, sketch an acceleration time graph. Okay? This would be a nasty question to appear, but I want you to be able to see it in case it does occur. As we get to the WACE exam, we'll look at there are some very nasty induced EMF questions of conducting rods rolling down ramps through magnets, and magnets on little carts that roll down through ramps through solenoids, and you've got mechanical, it gets tricky. All right, gentlemen, you have a few diagrams that I'd like you to complete. Determine the direction of the current induced, and then you've got these review questions. I need everyone to be 100% on Faraday's law, Lenz's law, and how you determine the direction. If you'd like to add some more tasks, you might wish to use the colloquial way of, well, Mr. Murray said that this side of the solenoid is going to say go away and it will become a north pole. So you could do it that way. Set up a north pole here because it's going to oppose the advancement. Set a south pole up here, and then figure out the direction that the current must flow to produce that induced magnetic field. So you can do that, but really I would want you to use the proper, what is the area bounded by the coil experiencing, figure out what Lenz's law opposes it. Yes?
Can you just explain something? I'm a bit confused. Isn't it the rings in the field?
Yep. Guys, you can work quietly. Come up to the front, and I'll do it on the screen, just for prosperity.
So,
all right, this one.
Yeah, so obviously it seems to me that the change is out of the page.
It is. Well done.
And that means that it's going to oppose it by going into the page.
Yes.
So the new ring, thumb goes in, fingers coil that way.
Well, hang on.
So the current goes...
Let me just use my little free hand. The change in flux that's experienced by this coil is going from into the page to out. Well, that's a change of out.
Yep.
So Lenz's law says that the induced must oppose.
Yep.
So now my induced current, fingers must be travelling into the page on that ring. Now take your pick, it doesn't really matter. We'll go down here and up there. So you'd get a try that again, clockwise.
Should be here.
Well, you've got it doesn't matter. During this reversal, the electrons would whiz through.
So clockwise, so if I said the change is out of, the opposing it has to be into, so it's clockwise.
Yep.
Okay.
Now, what I would tell you to do now is practice that fourth step.
Okay.
Yep. I mean, it's a lot of work to say Faraday's law, and maybe in the exam you just need lenses.
Yeah.
If you write Faraday and then lens, all right, they might not pay the mark for Faraday, but make sure you write it down.
Do them both anyway.
Yep.
I was very sick yesterday, so I didn't do any of it. Slightly out of the loop with
Yeah. Well, I did screen capture it.
Yeah, so...
And I think I put it up this morning.
Okay.
So sorry, I had cross-country training.
I wouldn't have watched it anyway, so I was out of it.
So,
Oh, no, sorry.
you can watch yesterday's lesson. I wasn't in a very good mood because we had lots of IT issues with the airplay dropping out. But you're looking at less than 15.
Less than 15. Right. Now, walk me through Faraday's lenses.
Yeah, pretty much. And we actually covered Faraday before the exam.
We did, yeah.
So lens
It's
is
like the full marketing that you want to have.
yes, yep, pretty much. Yo,
I'm just pulling everybody into the answers, and I just want to confirm this so I don't.
yeah, that's a good. All right.
Can you walk me through this one to see if I've got
B?
right? B.
Okay. Yep. Now to do that, I'm just going to quickly sketch. My field lines are always going from north to south. So I would say, as the magnet moves away, the area bounded by the coil experiences a change in flux that is left going to 0,
So that's a change in right.
which is a change in right, and so the induced
Left is left.
must be left. Then I put my pen down and go, right, inside that coil my fingers must be pointing left, which means my thumb's at the front, thumb goes up. Hey, what just happened? Thumb goes up.
And then this one's on this line, I assume, indicates the back one. So
Yeah,
it'd be X
that's
to Y.
yep. So X through to Y is the answer. Yes.
And which way is this going here? I'm not sure.
Okay. So since the field is increasing, we'll say blah blah blah. The area it's going from a small X to a big X. Well, that's still a change of into the page. Yep. That's it. So the induced flux will be in the opposing right-hand rule. Fingers must be coming out of the page, so our thumb will travel anti-clockwise. Well, now I've done them all for you.
I'll do the last one by myself.
Do it. Yes. No. Okay. So what I've treated this is the initial. And then final, because it's saying that the final's out of the page. So, or before and after. Okay.
So is it just 6.2 and not 6.3?
Just 6.2. Oh wait, where's 6.3?
That's the only thing we've done there.
Let me have a look. See. Hang on. Where's 6.3? Oh no. Yeah, you can do that. Come on, there's like 3. Oh. Do them all. Yes, get cracking. 10. Whoa, 10. There's 20 questions here. Man.
Look forward to it.
That's
Look forward to
mean.
every bit of homework we do.
Damn. All right, what's up?
This question.
Yeah. Okay. Let's go radio silence.